all of that technical issue. So basically, do I start now?
Yeah, please go ahead.
All right, thank you. And thank you guys for your patience on that. Today, we're going to be talking about comparing proportions and odds in SPSS. And the goal of today's lecture is to learn how to compare proportions using 2x2 tables and chi-square testing. We would also understand and interpret odds ratio using logistics regression. We'll practice how to transform variables and build models in SPSS. You might wonder why this is important. Well, many public health outcomes are often binary. So we're looking at a population of people and we want to determine, for example, if some group of people got vaccinated or not vaccinated. Some people have the outcome, maybe positive outcome for like HIV or negative outcomes. We also want to know how to compare proportions so that it helps us to evaluate interventions and access to interventions. Using logistic regression allows us to adjust for co-founding variables and make predictions as researchers. So now I have to share the screen. Oh, you just give me a minute. So we're doing all of these things in SPSS, right? And we have our data sets. I don't know if you guys have access to the data set already, but you should by now. So can you indicate that you have access to the data set?
Sorry, what's it called?
Yes, we do.
That's the resident doctor data set.
Yeah.
Yeah. And are you able to see my screen, the SPSS syntax screen currently?
Yes, we can see.
Okay, thank you. So we would start by bringing in our data. If you'd already downloaded the CSV file, this should be easy to get to. So you come into the file option, you right click or left click as you choose, and you select import data, CSV data, right? So I already have the data downloaded here. So it's called resident doctor CSV. And then you click on open. Take some minutes to get everything in and ready to go. Just click OK. And now we have the data set. I already had it open before, right? So this is it here. Something I always do when I'm working in SPSS is to name my data sets, just because if I'm doing lots of, using different data sets for different things at different times. So it shows that the active data set is data set 5, which is the one that we just opened. We named the data set. This is just the CSV file right here. It's nothing. You just name it and run. So now it's BS Stats Clinic, right? Again, another thing that is also important as you work in like coding and doing data analysis is to always, sometimes because of SPSS allows you to just do the clicking method, you can also like paste your syntax just to see what's going on in the background. So now we have our data sets, right? The data sets 5 titled SPSS. So we want to analyze and do the 2x2 tables. So what we first do is to go to analyze, right? Descriptive statistics, select crosstabs. Now the variable of interest, because we're trying to see the relationship between gender and marital status. So the variables of interest is the female variable that indicates whether a person is female, which is equals to 1, or a person is male, equals to 0. Maybe one thing I should also let us know before we proceed is, let's cancel this for a minute, is to look at your data. Whenever you bring your data in, you want to see what's actually there. You have an overview here that shows you the number of cases, that's the number of observations of people in your data sets. The total number of variables that we have is 10 currently, right? But we'll be creating variables along the way. We can see everything, so you make sure you know that everything is okay. So we go back to the analyze option again, descriptive stats, crosstabs. And now, like I said, our variables of interest and the relationships we're trying to see is gender and marital status. So we select female. as the row variable. Then the columns would be the marital status. So we are trying to see if an individual is married and what their gender is. We don't do so much here. We just click OK. And it gives us the distribution of individuals where 0 is male and 1 is female, and the marital status indicating 0 as not being married and 1 as being married. So just by looking at this now, we can see that we have how many people in our data set, 161 individuals like we saw by looking at the data, right? And we see that out of them, 65 men are married and 36 women are married, right? And 45 men are not married and 15 women rather are not married. So just basic 2x2 tables for this analysis. Then the next slide tells us to using the resident data, doctor's data set again, we're going to show the relationship between being married and gender, but this time we want to have percentages so that we can make better meaning of our data. We can say, oh, it's not just the count that we have now, we have percentages, and we can be able to present our results in a more meaningful way. So we are going to do the same thing we just did now. We go to Analyze, Descriptive Statistics again. We're selecting Cross Stats option. Because the variables we are working on are the same, if it was new sets of variables, you have to like maybe switch the variables of interest, and you can just select and bring it back or stuff like that. But that's not what we're doing. So I'm going to take age out of this. So now, because we want to see percentages, we select cells right here, and it shows us the percentage option. What we are interested in is the row percentage. We use the row percentage for interpretation of the outcome between groups. And in this case, our outcome is marital status, like I've said, and the groups we're interested in are the male and female groups under the variable gender. So you select row and you click continue and select OK. And what does it do? There's a slight difference now in our output, right? Here we had only counts, and we can just say 45 of 110 men were not married. But now we can more meaningfully interpret our data by saying, in this data set, we have 60 men that were married, 60% of the men were married, and 71% of the females were not married. So doing stuff like this, every time you're like, as a scientist or a researcher, and you're trying to like give counts, another thing that's very important is to look at the total number of individuals within the data set. In this population, we can see that we have more men than females. So does it really make sense to say that we have 71% of, we had more higher percentage of married men compared to female to married women? Maybe, maybe not. But when you want to write your results, you can now say something like, in our data or in our sample, we had 60% married men that were married, where N is 65 all over 110. So now you're showing the sample that was married across that group of 110 men. And you do the same for women and say we had 71% of the females were married with a sample size of 36 over 51. That makes for more meaningful data interpretation. Do you understand this? Should I proceed, or do you have any questions at this point? I'm sorry I can't see you guys, so you would have to help me.
No, sorry. I just have one question from the coding. Is the coding one for female or one for male?
Sorry, I didn't hear you.
Sorry, the code, the variable, the codes for the variable.
Yes.
Female. The one for female, the one for male.
Yes, we can actually do something here. So again, because the way the data set was just like downloaded, and we can label our data, right? In the variable view, you can come here and say, first you can just edit and say gender, right? Then you can come to the values option here and select, and you select and say the value 0. We know the value 0 represents the men, so we say male. 1 represents female, right? This way, it helps better to interpret. So if we decide to rerun the crosstabs again and just see, now you can know, and let's do the same for the married. So we say marital status. You just edit right in SPSS. That's one of the benefits of SPSS. There's a lot of easy to do stuff that you can just get done. We know 0 is unmarried and 1 is married, right? So click OK and it's done. So now we will run again just so that you are able to understand what you're actually looking at. And that's a very good question. Thanks for asking. So we have everything already again. Just click OK. Now it's better, right? Does this help?
Yeah, it does.
Yeah. So basically, it's always good to have a data set that is complete, not just with like the values, but also the interpretation, so that when you come into the data, we can like decide to like label and add lots of values to all of this. So it helps for more meaningful interpretation. So let's proceed. Now, we are going to also do some chi-square testing. Remember, we started with just having counts, then we had percentages. Now we want to do chi-square testing. We're using the same data sets, right? But why do we do chi-square testing? We do chi-square tests to help us analyze the relationship between categorical variables in a data set. And we have key outputs that we are now looking at beyond just numbers. We are looking at whether there's any meaningful association between the predictors, which is the gender, and marital status, our outcome. So what do we do now again? We come back to the same data set. This time we say analyze again, descriptive stats. You do the cross tab, right? If you see, because we're still doing the same thing, we have the same sets of variables. The cells are still highlighted as row. If you're still interested in seeing that, you can go ahead. If not, you can uncheck this and click continue. But one more thing we do is to select statistics, right? Right here in this window, you see statistics. You select chi-square. Simple as that. You select continue and say OK. So now, this is our output, slightly different, right? We still have the counts, we still see the percentages, but we have something else that adds to this data for interpretation. We have the chi-square test, and we have the significance value of 0.160. What does that mean in making maybe a prediction or deducing like whether or not there's a statistical significant relationship between being female or being male and being married? So at the chi-square test and p-value of 0.160, we will fail to reject the null hypothesis, because our null hypothesis was that there is no difference between being male and being female and marital status, right? But now we see that there's actually no difference, because this data set is showing us that there is no difference. If there was difference and we had a p-value that is less than 0.05, then we reject the null hypothesis, right? So in making meaningful interpretation of your data, chi-square test helps us to see that relationship between our predictors and our outcome at different significance levels. Most times, the baseline significance levels that we use in research for public health research is 0.05. So if the value here was, let's say, 0.021, or you had 0.019, you can now say that there is indeed differences between these two groups, that's the male and the female. Sometimes you might have a p-value of 0.059, and there's always the argument, do you consider that as being statistically meaningful or not? Well, for my interpretation and what I always do, if I have a p-value here that's 0.059, I would still fail to reject the null hypothesis, because 0.059 when rounded up is 0.06, and that is higher than our significance level of 0.05. So the next thing we're going to do now is to practice on our own. Did you guys download the menopause CSV file. I just need a response if you guys downloaded this menopause CSV file. Or do you know where to download it from?
Yeah.
Okay, so you download this file, right? And we're going to do the same thing we've just done up until this point, which was we brought in the data, right? And then we would also do the 2x2 tables, right? We'll do the 2x2s with the percentages, and then we'll conduct a chi-square test to assess the relationship between the variable surgical menopause and testosterone. Now, the instructions are here. Imagine that you are the statistician on a trial of testosterone, and you want to treat, the testosterone was to treat low libido among postmenopausal women that are not taking estrogen. Now, there are 811 women in the sample, and they were randomized to receive testosterone, 3 micrograms of testosterone, and 150 micrograms of testosterone, or a placebo. So they were randomly put into different groups. And then the variable testosterone identifies the women that received the testosterone shot and those that did not. So you will have 0 and 1. Then also you will see that there's another variable that says whether the women attain menopause as a result of surgical procedures, and they can be identified by the variable surgical menopause, right? So let's take some time to bring in that data set and create our 2x2 tables and chi-square test. I think I'm just going to try to see you guys because it's not helping that I can't see you. So how do I do that? And so are we trying to do that currently?
Can you please share the question?
Yeah.
We can see the question.
Again, right. I was just trying to make sure that I can see you guys, but I can't. So anyways, this is the question here. So we give an additional like 3-4 minutes. What do you guys say to get this done? How close are you to doing this? Does anybody have any results?
Yeah, good evening. Please, can we get like a PDF file or like a presentation to show that question so I can work with it?
So are you not still able to see the question right now?
No.
No.
Oh, apologies about that. I thought you could. But it should be showing this screen. I thought I'm sharing my screen. You can't see my screen. What screen do you currently see?
We can see your screen, or your screen showing the SPSS file.
The variable view.
Okay,
Yeah, very
sure.
movie on SPSS.
Okay.
The file is on the classroom in the coursework section. It's SPSS Lab 4 in the classwork section.
Okay.
If someone is
Okay.
Okay. So let's just proceed, right? I'm hoping that you've been able to download the data set at least, and you brought it into SPSS, right? And so doing the same steps that we just did using the resident doctor data sets, we're going to create the 2x2 tables, right? Then we will do the chi-square test for this data. So again, we do the same thing. Please, can you indicate that you can see the SPSS screen?
Yes, we can.
Okay, thank you. So descriptives again, cross tabs. Now, we want to see the relationship between surgical menopause and testosterone levels, right? So surgical menopause.
I think you need to zoom a little bit because it's so small that you can't see.
I'm sorry, I can't zoom. There's no way to zoom. Just
Please, which data set is that?
You can zoom from your screen. Like if you widen the parts of her screen, it would zoom.
let's see.
Please, which resident doctors? The one I have, the one that we've been using before is not like this. Is it new one? Please.
You don't have the resident doctors data set?
I had it before, but it's not like the
one I'm
when
trying to show. Yeah, this is a new data set just for you to practice. It's called the menopause CSV file data set.
Okay, thank you.
Yeah, you should be able to download this. We said to increase this. I'm not sure that I can actually do that on this computer.
Sorry, no, ma'am, not you, the presenter. I was saying that those of us who are viewing can increase it from our own end.
Oh, okay, okay. Thank you for that. Okay, so we're going to proceed. So we're doing the same thing. We want to create a 2x2 table for the variables, surgical menopause and testosterone. Like I said, you brought in your data like I did just now, and you can see the variables. This is the data for each of the individuals. And our observation, we have 811 women in this data set as the instruction indicated, right? And 6 variables. So we come to analyze and we do the crosstabs of surgical menopause by testosterone levels. So we click and just bring, this is just to bring the data into the right, the variable into the right either row or column that you're interested in. Because we're not looking at the percentages yet, right? We can also, let's just look at the percentage. It says 2 by 2, so we can look at both the count and the percentages, right? We click continue and we click OK. So now, one thing we didn't do like we did the previous time was to label 0 or 1, but just so that you know, 0 indicates that they did not take testosterone shots, right? Or they were not given, and 1 indicates that they were given. And 0 means for the surgical menopause variable, 0 is that they had surgery procedure, and that was the reason why they had menopause earlier, or they did not have, which is 0 for not having, 1 for having a surgical procedure, right? So in this data set, we see that 377 women did not have the surgical procedure, but they did collect testosterone shots where 1 indicates that. And the percentage is here. You approximate this to 64%. You can make the same deduction by looking at the count of yeses, which reflects 1. 1 reflects counts of yeses. And we can also say that among the women that did undergo surgery, 134, which is 61% of them, got the testosterone shots. This is just the 2 by 2 table, right? So now, if we are going to do our chi-square test again, we do the same thing and do descriptives, crosstabs. Our variables are already in the right places, so we select statistics and indicate chi-square, right? And select continue. Select OK, and then we have our chi-square testing of 0.513. So there's no significant relationship between whether you go through the surgery or you have testosterone, you took the testosterone shot, because this p-value is higher than 0.05. I should not be interpreting for you. So the next time we run either a chi-square test or a regression as we proceed, 1 person in the class is going to help make meaning of our interpretations. So now our next phase of the lecture is on logistics regression. Why do we do logistics regression? We do it for many reasons. 1, to estimate or predict. We do it because of the types of variables that we're working with. We do it when we want to adjust for co-founding. So for the estimation or prediction, some of the tests that we did before, like chi-square test, just tells us the difference between groups, but they don't tell us how strong the relationship is or help us to make predictions. What logistics regression does is to help us to estimate the odds of an outcome within a population or groups of people within a population. So for example, yeah.
Can I just interject a little? I just have one question before we move to the logistics regression. So yeah, like you said, chi-square is best used for categorical variables. So in this case, we are not measuring any means, we are not on all of that, right? So, but we do know that categorical variables can be either ordinal or nominal. For what you have used, it appears that the variable we used are nominal, right? So just picking those that were treated or those that received intervention or not. What happens in the case of ordinal data?
You still interpret the same way and say, for example, you have ordinal data of satisfaction levels, a group of people within the variable. So we say want to see the, let's say among those that got the shot or went to a clinic for care, for example, and you want to see how satisfied those group of people are with the care that they receive. and we have orders of very satisfied, not very satisfied, neither satisfied nor dissatisfied, dissatisfied and very dissatisfied. That's the order, right? So you still interpret the same way.
Yeah.
But in that case, most times that's where the logistic regression comes in, because then you have to have like a reference category or a reference group within that category. So we can compare, right? And you can also as well just do the chi-square test and just say within this group. But most times the best thing to do is to do a logistics regression, because then you can reference that and say, let's say, for example, it was a logistics regression we did. I want to look at having done the surgery versus not doing the surgery, right? So we can say among this group of people, compared to those that did not take or undergo the surgery, those that did go through the surgery had higher, and we're just jumping to the next step, which is the logistics regression, had higher odds of getting testosterone shots. Does that answer the question?
Okay, so you said logistics regression.
Yes.
Okay, that means
because it allows you to do more comparisons, right, across the groups or within group comparisons. Does that explain it? Does that explain it? Can I proceed?
Yes, please.
Okay, thank you. So as I was saying that we do logistics regression for many reasons to estimate, right? And I was explaining that it allows us to estimate the odds of an outcome among groups of people, right? So for example, we want to, like from the data set we were working on, which was the resident doctors data set, we want to see the odds of maybe being of female gender and maybe taking some work hours. We're going to see that in an example. Or we want to see how much likely does smoking lead to the development of hypertension disease. We also use it because of the flexibility in our predictors, right? So it can handle predictors that are either categorical or continuous, right? So if you want to study, for example, how age affects the odds of testing positive for a particular disease, like the outcome of HIV, you do logistics regression, as well as adjusting for confounding variables. So for example, we want to see the odds of smoking on having hypertension among individuals that are, for example, diabetic or working in a particular industry. So we include many variables within our model to just predict the outcome smoking and the outcome of hypertension and smoking on hypertension. Let me just rephrase again. So like I said, we have many variables because there are many things that can cause a disease. You can be exposed to smoke from just going about working in the environment or working in an industry. You can as well also be a smoker, so you smoke cigarette. And we want to see the risk of developing hypertension among smokers. But we are aware of the fact that within the environment, people also get exposed to smoke from other sources aside cigarettes, smoking from cigarettes, right? So we include all these variables in our data set, but our major predictor variable is smoking cigarettes, and our outcome is hypertension. But we are going to put all these other variables like age, gender, exposure to smoke from other sources. For example, we were conducting the research among individuals that work in a factory that are exposed to smoke, but we know that within those population as well, we have people that actually smoke cigarettes, right? So we include all of these other variables, but our main predictor variable is smoking cigarettes, and the outcome is developing hypertension. But we are adjusting for all the other things that can actually also predict or cause the outcome of hypertension. That's what logistics regression helps us to control for all of these things and make more meaningful interpretation. So going as well, we also know that there are other different tests that we can do aside logistic regression, like linear regression. But the differences between logistic regression and linear regression is that logistic regression allows for modeling of binary outcomes. What do I mean by binary outcomes? That's what we've been working on since we started the lecture. We have outcomes, testosterone. We had outcome, marital status, 0, 1, yes, no, satisfied, not satisfied, HIV positive or HIV negative. So in public health, most of the time, our outcomes are always binary like that. And we want to know if a person has the odds of saying yes or being positive or being very satisfied. So we use logistics regression for that. It also helps us to estimate, but it doesn't predict a number. It predicts the logs of an outcome, the log odds of an outcome. For example, when we have a odds ratio greater than 1, we can say that an individual has higher odds of the outcome versus when they have the odds ratio less than 1, and we'll say that that individual has the lower odds of the outcome, as well as testing for goodness of fit. In linear regression, we can check how well the model fits using R-square and residuals. We're not really bothered about that in this lecture, but in logistic regression, we can use different tools like the chi-square modeling to see if the model improves because we added certain variables. We can also get the pseudo R-square that gives us a rough idea of the fit of the model. So basically, when do you use logistic regression? When your outcome is binary, tested, not tested, vaccinated, not vaccinated. When you want to predict the odds of something happening in a group of people within categorical variables. When you want to adjust for other factors like I explained with the smoking scenario and the outcome of hypertension. And also when you want to quantify the strength of the association using odds ratio. Any questions? None. Okay, we'll proceed. So we're back to our resident doctor data set. Just to make sure that that's the one we are using. Excuse me. So we want to first, like I showed you earlier on, right? This data set currently has continuous predictors here for marital status, and let's say we want to see hours worked. That's the workload score, right? So this workload is showing this hours worked, right? That is the variable of interest, hours worked, excuse me. So it shows the hours individual work in a week. We can see that there are people that work for 80 hours, some people work for 50, 70, 91, and so on. So right now, it is our outcome of interest, but it is not yet in the way we can use it for logistics regression because it is continuous. And again, remember that in logistics regression, we want our outcome to be binary, right? So we want it to be either, if we have a threshold for this data set, we want to look at people that worked more than 70 hours. That's our threshold. So anybody that works less than 70 hours would represent the 0 category within that variable. And anybody that worked more than 70 hours will be represented by one within that variable. So we want to transform this to not have just continuous numbers and make our outcome binary. So we're going to transform, select transform, recode into different variable. Then we're going to bring that to the screen. Then we select hours worked, which is the variable that we are transforming. Bring it into here and you name it. We are going to name this new variable that we are bringing into our data set as, let's say, as GT70. We can decide to label it to give it a meaning, and we can just say working more than 70 hours per week, right? You select change. So now we have, what this is doing is it's bringing this variable hours worked and creating a new variable, creating a new variable hours GT70 from the variable hours worked, right? We selected change. You select here old and new variables, okay, right here. Remember that our threshold is those that either worked more than 70 hours in a week or less than 70 hours in a week. So we select here range value through highest and type 70. Then you come here under new value and we say 1 as the new value, select add. So individuals from 70 working 70 hours and above are indicated as 1. But we want to also reflect those that work lower than 70 hours, right? So we say all other variables and select, type in here 0, and you see hard. So we're telling SPSS that if an individual works less than 70 hours, whether they work 69 hours or 50 hours, all those individuals should fall within the group 0. You select continue, click OK. Now, remember when we started, we had 10 variables in our data sets. Now we have 11 variables. And this right here is our 11th variable. This new variable we created, hours GT70. And we have our label that helps us to make better interpretation, which is working more than 70 hours. So we can also decide to help ourselves and say 0 indicates no, add, 1 indicates yes, where a person worked more than 70 hours. Select OK, and now we have that, right? So we've transformed the variable. You can do this with any other variable that is continuous and you want to make it into binary outcomes. Any questions on transforming variables? Okay.
I'm good.
Okay, thank you. So we continue, and now the instruction tells us to use this same data set and this new variable that we've just created to do a 2x2 first. We do a 2x2 table with percentages, and now we want to determine if working more than 70 hours is related to individual's gender, right? So we're going to do that crosstab again, and now we're going to see what we get. So we're doing the same thing, analyze, descriptive, crosstabs, right? Now, our role still remains gender, but our outcome variable is changing, which is our column, right? So we're putting that back. Marital status, we take it out of the chart and bring in working more than 70 hours per week. The new variable, 70 hours GT70. And bring it in here. We want to see the percentages. It's already highlighted, but imagine it wasn't. You just select row, and it helps you to see the percentages of individuals within that sample that worked 70 hours or more or less. So you select OK. Sorry, this did the chi-square. We should not be seeing the chi-square test now. But anyways, this is the output that we're interested in. The 2x2 table of working more than 70 hours in a week, yes, no, across the variable gender, male, female groups. And we see here in our data set and our sample that 55% of females worked more than 70 hours in a week, compared to men that had 74% who worked more than 70 hours in a week, right? So that's just why we needed to transform that variable, because it was currently just continuous with numbers, but now we've done something more different, which is to make it into a binary outcome of working more or less, and then still making meaning of our data. So next thing we're going to do now is the logistics regression to determine if working more than 70 hours is related to gender. This time around, we're not going to use the descriptive stats or crosstabs function. We're going to select here regression, binary logistics. That's where we come to. Now, when you want to do this, you need to know what's your dependent variable and what's your independent variable. Because the relationship we're testing is the relationship between gender and our outcome working more or less than 70 hours. So the dependent variable for this analysis is the variable 70 hours because it is dependent on gender status, right? So we select here working more than 70 hours and put it here. Then our covariate, which is the predictor variable, the independent variable. There are different ways you could call it, independent, predictor, what have you. And we put the variable gender in here, and that's one. Now we select categorical here, bringing that here, right? And bring the gender variable into the categorical covariate right here. Now, most times you don't have to do anything outside of this and just click continue, paste and run. But there's this, and that's bringing us to the question we asked earlier. Now I was trying to explain it. There's the option to select a reference category. There has to be a reference category because you are trying to you're trying to compare, right? So we're trying to compare males and females, but we need something to rely on, which is when we're making the interpretation, so we can say, oh, between group A, compared to group A, group B had this, right? Using group A and group B as a reference category or using group A as a reference category, and you can choose whichever group you want to use. For this, we're sticking with what is, which is the first. We tell SPSS to select the first group within the categorical variable gender. And our first group, if we recollect, is male because they are the 0 group, 0, 1. So it picks the number 0, 1. If you have 5 different groups within, let's say, the variable satisfaction with care, for example, and I said we are very satisfied, not very satisfied, dissatisfied, neither satisfied, those are different groups. If I decide to use, for example, the last group, which is maybe dissatisfied, I'll just select last. But it's going to pick it according to numbers 0, 1, 2, 3. So you have to be specific on what group you want to use as your reference category. We're using the male, which is the first group. So we select OK. Right. Now, our output is large. There's a lot that we see here right now. And we're going to try to make meaning of that data shortly. So let me just bring us to that slide. So we want to interpret, we've got different outputs, right? What we're very interested in, we still see, you just want to check how many people were included in the analysis, was there missing cases, and all of those basic stuff. But this is where we make this is what our result is dependent on, and we make interpretation based on it, right? So our null hypothesis was that there is no difference, right, between being male and female and working more or less than 70 hours in a week. Our output here starts with the B coefficient, which is the log odds that tells us the difference between males and females. And our log odds here is minus 0.830, right? So we have a negative value for the odds, and a negative value indicates lower odds for the group female. The gender here is 1. Remember that we had said to SPSS to select 0 as the reference category. That is why we would not have any output for the 0 group within the gender variable, right? And we have an output for the 1 group, which is the females within this gender variable. If we had more than 2 groups within the gender variable, it's going to list and say 1, 2, 3, 4, for example, while recognizing that there's a reference category that we had selected, which is the 0 group, right? So first, interpretation is dependent on 1, this is the B coefficient that tells us the log odds of the difference between males and females, and a negative value indicates lower odds. And here we can say that females have lower odds because we have a B coefficient of minus 0.830. Another thing that we want to look at is the odds ratio that is denoted by this exponential B outputs, right? And our odds ratio here is 0.436, which tells us that females within this data set have 0.436 times the odds of working more than 70 hours compared to males. That's what it tells us. That's what this 0.4. So it tells us that's the odds ratio we're interested in. So if you are writing a paper and you want to determine the odds ratio, you look at the exponential B to report your odds ratio. Another thing we want to see is whether this association is statistically meaningful, so that we can either reject or agree with the null hypothesis. Again, our null hypothesis is that there is no difference in the odds of working more than 70 hours between being male and being female as a resident doctor. But now we see that our odds ratio is less than 0.05. We have a odds ratio denoted by the significance p-value of 0.019. So we reject the null hypothesis, because now we see that there's a difference between being a female resident doctor and being a male resident doctor and the number of hours that the person have worked, right? Another thing we can do, because we have a odds ratio of 0.436, which is less than 1, what we do is to subtract it from 1. We subtract that odds ratio of 0.436 from 1, and we multiply our results. So when you do that, you should get about 0.4564. 1 minus 0.436 will give you 0.564. You multiply it by 100% and you get 56%. So we can say that the female resident doctor's odds were about 56% lower compared, because again, our reference category are the male residents compared to the male resident doctors. Are we following?
Sorry, can I ask a question?
Yes, please.
Sorry that I didn't just want to interject.
Mm-hmm.
So 2 points. Why is the hours work being the dependent variable instead of okay, so that is dependent on something that is already established, right? So because males and female is already there, it's a variable that does not change. So for instance, if respondent or observation number 10 is a male, it cannot change to a female. Just thinking around my head.
Yes.
But then looking at the variables in the equation, the logistics regression itself, the significance is 0.195. I would think that 0.195 is actually greater than 0.05. Or am I wrong?
It's 0.0.
This is 0.019. Yeah, so if I want to approximate that to 2 decimal places, it becomes
0.02. Yes.
Instead of 0. So 0.02 is actually greater than 0.005. Or is it 0.05?
It is
0.005.
It is 0.005.
Okay, so that would mean that this value is higher than 0.005, which would mean that we would reject the null hypothesis.
You reject the null hypothesis because it is less than 0.005.
No, let me clarify. I think that you might be, sorry, 0.0510, not 2 zeros.
Oh, that's why I was confused. So 0.05. Yeah, so 0.019 is actually less than. Yeah, so
yes,
we reject, or we
reject the null hypothesis.
You say what?
We reject the null hypothesis.
Well, madam, are we not comparing this 0.05, not 0.005?
It's 0.05, you're comparing 0.0192. When you approximate 0.019, it becomes 0.02. And you're comparing it to 0.05, which is our alpha, our statistical level.
Because I heard like 0.005. That's why I was.
Oh, my bad. If I kept saying 0.005, I apologize. It's 0.05 I meant to say. And that's the significance level that we are comparing our p-values by, or to rather. So it's a p-value of 0.019 is less than 0.05. So we reject the null hypothesis because now there is difference between working more than 70 hours and being either male or female.
Thank you.
Is that clear?
Yes.
Thank you. So,
sorry, please, I have a question, please.
mhm.
I don't know if you could just take that odd ratio, how you got the percentage of 56, when you subtracted 0.436 from 1, and you multiply 56. Can you just take that again, please, the odd ratio, please? Thank you.
I said that, so when you get your output, the things that you're interested in, like I explained, we had the coefficient, beta coefficient, the exponential B, and the significance level, right? We can already infer from this output that women have lower odds, or female resident doctors have lower odds of working more than 70 hours compared to men because of the negative value minus 0.830. Again, we have a odds ratio of 0.436, which is the exponential B output that we have here, meaning that females have 0.436 times the odds of working more than 70 hours compared to males. You can actually decide to just end your interpretation there and say that you reject the null hypothesis because our p-value was less than 0.05. Now, another interpretation that we can give is to subtract our odds ratio from the value 1. Because it is less than 1. If it was greater than 1, we would do something different, which I'll be explaining in the next slide. But because it is less than 1, we subtract it from 1. So we minus 0.436 from 1 and multiply that result. So if you have a calculator and you just say 1 minus 0.436, you should get the value 0.564. Multiplying that by 100% will give you 56%. So we now say and interpret furthermore and say the female resident doctors' odds were about 56% lower than the male resident doctors in terms of working whether more than or less than more than 70 hours a week rather. Does that explain it?
Yes, it does. Thank you.
Yeah. So, like I was getting at, we have other ways of measuring and comparing across groups. We have relative measures that includes the hazards ratio, the risk ratios, and the odds ratios like we did. So they help us to compare the likelihood of an outcome across or between groups. So we can say things like group A is more likely to have an outcome or experience the outcome compared to group B. Or we can say group D had lower odds of the outcome compared to group E. When we are conducting different analysis, we use different ones of these relative measures. The hazard ratio can help us to measure the rate of an event over multiple time points. It's called time to event analysis. The risk ratios compares the risk of an event happening in 2 different groups, while the odds ratio helps us to measure the odds of an event occurring in one group compared to the odds of it occurring in another group, which is what we have been doing. Sorry?
Please take that again.
Okay. Where? The odds ratio, hazard ratio, risk ratio.
Yeah, the 3 of them.
Okay. I said the hazard ratio helps us with time to event analysis. So it helps us to measure the rate of an event over multiple time points. Because when you do research, sometimes you collect data on day 1, and then you have your intervention, and then go back to that same population and collect the same sets of data at maybe day 30 after your intervention. So you want to see if there's been differences within the group, within the population across these time points regarding the intervention you have just prescribed, right? The risk ratios helps you to compare the risk of an event happening in 2 different groups, while odds ratio measures the odds of an event occurring in one group, like we just did, the event of people working 70 hours or more in a week across the two groups, male and female, right? That's what the odds ratio does. And that's what we have been doing since. So we have this chart here, and we have different use cases and different interpretations that we can deduce from the occurrence of the outcome. Our outcome here is the tendency for people to, which gender reads more to their children. Is it women or men? And we have different constructs, like values, like we did here. We had a value of 0.436. That's the odds ratio we had. So like I was saying before, you know, we got the 56% because we subtracted it from 1. Imagine we had a situation where we had a odds ratio of 1.4 or maybe 2.5, whatever the case is. What do we do then? Do we still subtract it from 1, or we make a different decision? When our value is greater than 1, but is less than 2, so we have 1.4, 1.8, 1.9, what we do is that we subtract 1 from that value that we got. So in this case, we had 1.4 as our value. So it is greater than 1, but is less than 2. So we subtract it from 1. We subtract 1 from it, rather. So we have a value of 1.4 minus 1, and we'll have 0.4. So you multiply that 0.4 by 100%, and you can interpret it and say more likely. So we say women are 40% more likely to read to their children than men. Because again, we have a value of 1 that is greater than 1, but is less than 2. So we subtract 1 from that result. If, like we just did, we had a value that is less than 1, like 0.436, or in this example here, we have a value of 0.83. We subtract that value from 1. The first case, we subtracted 1 from our value that was higher than 1, but less than 2. This time around, we're subtracting our value that is less than 1 from 1. So 1 minus 0.83 would give you 0.17, right? And what does that mean? So we multiply again by 100% and interpret using the language or term less likely. So we then say women are 17% less likely to read to their children than men. Again, if we have a value, say, greater than or equals to 2, 2.3, 4, 4.6, whatever, we don't do anything. We don't make any subtractions like we did in the previous 2 steps. And we just say, or use the term times, so times more like this. So we say women are 2.3 times more likely to read to their children than men. So to sum it up, we use odds ratio and we get it from logistic regressions, like we've been doing. Risk ratio, we get it when we use it when we're doing cohort studies. Hazard ratio, we use it in survival analysis or time to event analysis, where I gave an example of either we are comparing across different time, or we want to see how something changed between point time A versus time B, or time C versus time D. Does that help? Do you understand what I've just said?
Sorry, the whole thing played in my head. If I would just ask, I understand the concept of the hazard ratio being time to point to time estimate. The odds ratio, you said, is the likelihood of the expected outcome or the very outcome of interest occurring in one group against it occurring in another group, right? Okay. But then the risk ratio would be, can you just remind me, the risk ratio?
The risk of an event happening in 2 different groups.
So how does it differ from the odds ratio?
It differs because we're looking at risk. The odds ratio helps us to measure the odds of an event occurring. So because sometimes you don't look at risk, you look at the odds. How many more times likely is this thing going to happen? Versus what is the risk of an individual developing this outcome because of, for example, we had said we wanted to look at the risk of, say, smoking and developing hypertension. So what is the risk of you as an individual? Because you smoke 2 packs of cigarettes per day, what is your risk of getting hypertension versus the risk of an individual that smokes 6 packs getting the same outcome? But the odds ratio helps us look at the odds of that event happening as well. So the odds of a person that smoked, odds of smoking status on the outcome, hypertension. Does that help? Is the risk of an event happening? That's the risk ratio. That one, odds ratio does the odds of it occurring. Most times they are used interchangeably, but the interpretation varies.
Okay, so it means we can actually check the risk and then go ahead to check the odds.
Depending on your research question.
Yes, depending. Okay. Yeah.
So we had also done the whole, I had said that one of the benefits of doing logistics regression is because it allows us to control for other things that are factors that can actually affect outcome. And I've given us the scenario of, an individual that smokes and works in a factory that emits a lot of smoke, or works in a motor park and they are exposed to smoke of exhaust from vehicles and developing hypertension. So there are many things that are at play to an individual developing an outcome. When you go to the hospitals, they would ask for other likely diseases that a person has. You can be complaining about having a headache and they want to check if it's related to maybe some traumatic brain injury because the person had an accident. But we also want to ask, have you ever fallen before? Because now you're having a headache, you've had a fall. Could you having TBI, traumatic brain injury, be related to you falling? Or is your TBI outcome that we are trying to predict associated or related to you having a headache? So there are many factors that predict an outcome. But sometimes we just want to look at one, but we can't ignore that these other factors exist. And that's why we use logistic regression to help us to control for all of these other things that can also potentially impact the outcome. So we are going to do something slightly different because the previous logistics regression we did was just looking at gender and working 70 hours. Working 70 hours or more in a week, right? We're going to now look at this same association or relationship, but now considering the fact that individuals are married. So marital status enters into the chart. We know that most times, because a person is single, they might have maybe more hours to work or even less hours to work because they have to go do certain stuff, right? Compared to someone that is married that also has a family to tend to and would want to work more hours to get more pay. So we're going to factor in all of this in predicting the relationship between working more than 70 hours in a week and your gender. So, and again, we're going to do the same thing, but slightly different. So we still come back to regression, binary logistics, because we're working with the same set of variables. It's mostly everything in here. We already have working more than 70 hours. We have the predictor variable, which is gender, denoted as female, and has categories or groups 0 and 1, where 0 is male, 1 is female. Now we bring marital status into our conversation and include it here. Right. Then you come here to categorical. Because marital status is now in the chart and is serving as a covariate, you also include it here and just bring it, doing the same thing. If none of these things were, imagine we had not already pre-filled our columns and already predicted which is the dependent or independent variable. You have to just manually select from here and just make sure everything goes to the right place. You select continue, and then you select OK. So this was the last output we saw, where we saw gender and marital status, right? Now we're going to interpret this new output that we get. So it was just gender and working more than 70 hours. Now we have gender and marital status. Because, again, the reference category is we said SPSS should use the first group within the variable, which is for the gender variable, male. And now for the marital status variable, what was the first group in our variable? We can quickly check. Unmarried is the first group in our categorical variable of married. So we go back to our output. Just a minute. So yeah, we're going to make some interpretations, but we're still very much just concerned with the relationship between gender and marital status. That's what we're still trying to predict. Again, we start by looking at our output. We have the beta coefficient, right? And now it's still having the negative value, but slightly different from 0. I think we had 0.830 now. We have 0.870, but still, we can still say that the log odds and the difference between males and females is that females have a lower odds of working more than 70 hours compared to male, because it is denoted, we have a negative value here that denotes lower odds of the outcome. We also look at our odds ratio. We have an odds ratio of 0.419. So we'll say that females have 0.419 times the odds of working more than 70 hours compared to male after adjusting for their current marital status. Before we didn't, because before now, the previous one did not have the marital status variable in the equation. So we didn't compare, we didn't say, oh, because we control for marital status, we can deduce that this is our relationship. But now we are taking to note that after controlling for all these other factors that can potentially impact an individual's ability to work more than 70 hours a week, we can confidently say this is the odds ratio, which is females having 0.419 times the odds of working more than 70 hours compared to males after we've controlled for the fact that they are married, which is our marital status variable. We've controlled for that, right? After adjusting for current marital status. We also see that the p-value here is less than 0.05. So our p-value is 0.016, and it is lower than the alpha value of 0.05. So we still reject the null hypothesis that had said before that there is no difference. There is difference. Our output is telling us there's a difference because of the p-value of 0.016 that is less than 0.05, right? So we conclude then by saying that female resident doctors in our sample had lower odds of working more than 70 hours a week compared to their male colleagues, controlling for or adjusting for one of those two terms would be used for their current marital status, and then we conclude our analysis. But when you are like creating your results table, the most important thing that you put in there, you can either report the log odds, but you have to report the p-value and you have to report the odds ratio. I generally report the odds ratio and the p-value just to help like with my interpretation. And that should end the conversation for today. Don't know if you have any questions or takeaways from the class. For some of you that were not able to like work with the menopause CSV file, I hope you're able to do that. And I hope this class has been able to like teach you one or two things about comparing odds and proportions when conducting research as a public health or research scientist. Do you have any takeaways or questions?
So sorry. Lastly, before Tabitha, you said in the result table there's like no need to report on the p-values of the co-founders, right? Because I'm seeing that the p-values are even more than The p-value for marital certainty is more than 0.05. So there's no need, it doesn't matter, right? We're just looking at how it affects the p-value for the variable of interest. Right?
Because the relationship we want to predict is the variable of interest, gender, marital status. If we were going to say that, let's say we have a data set, and because gender, marital status, age, employment status, education status, all of those things are demographical variables, right? And our research question is saying that we want to predict the relationship between marital status and demographic factors, individuals' demographic factors within the data set. So we would report and talk about the other ones, the other demographic variables like marital status, age, and all of that. We'll report that in our table and our results section. But because for just this use case, we're only interested in gender and working more than 70 hours. If I said we want to see the variables that predict, or the factors that predict rather, working more than 70 hours, and we include all of these things, including gender, marital status, what else do we have here that could be a demographic variable? Age, having kids, that's children, right? And age has been categorized here. So yeah, satisfaction with job is also a variable. We want to predict that on the outcome of, or the relationship between all of these on working more than 70 hours a week. Then we'll report all of those things. And for this case, we would say that because the p-value is greater than 0. Where's the output? Because the p-value is greater than 0.05, we will fail to reject the null hypothesis. Does that explain it?
Yeah, thank you.
Yeah, thank you.
Okay. I'm sorry, I missed it when you were interpreting the odds ratio, when it is below 1, when it is above 1, and when it's above 2. I missed that because I lost my network this side. Can you please go through that?
Yes. So I said if our value is more than 1 but less than 2, we'll interpret it as an individual having, for example, we have a value of 1.4, right? 1.4 is greater than 1, but is less than 2. So what do? We subtract 1 from 1.4. That's the first thing we do. Then we multiply it by 100%. And then because of our outcome here is reading to children, so we now say that women are 40% more likely to read to their children compared to men, or than men. If we had a value of less than 1, we will subtract that value from 1. The first instance we subtracted, we'll subtract 1 from that value, rather, I keep putting it. So the first instance, we subtracted 1 from our value because it was higher than 1, but less than 2. In a situation where we have a value less than 1, we subtract it from 1. So in this example, we have a value of 0.83. So we subtract it from 1, and we then have 0.17. So you multiply 0.17 by 100%, and you now interpret as women are 17% less likely to read to their children than men, because the value we got originally was less than 1, right? If we had the value that is equal to or greater than 2, for example, we have a value of 2.3, we don't do anything, we don't make any subtractions. We just say that women are 2.3 times more likely to read to their children than men. Does that help?
Thank you. Yes, it does. Thank you.
Okay. Any more questions?
Sorry, you made reference to 17%. Which variable are you looking at?
No, this was just an example. Like
okay.
there's no data set here that's looking at that. I mean, we didn't do that. We're just giving vague values and just inferring different outcomes.